Okay, so last time we discussed cosmology, and everything comes from these equations. They really contain virtually everything we have to say about cosmology. Different people get their names attached to some sub-equations of Einstein's equations, but you don't really need to remember that. This is the only equation you need to remember. And most of these equations are consequences of those equations. So we took the 0, components of the Einstein tensor and computed it. Remember, we assumed the metric was this. Okay, where this was S3, E3, or H3, and these correspond to K equals +1, 0, or -1. Okay, and as I explained, one should really think about the curvature radius of the universe, or the inverse curvature radius squared. Let's call that 1 over r curvature squared is equal to k over a squared. So you're free to sort of rescale the spatial coordinates and a, and that changes the scale of the sphere, or while keeping the sphere the same, let's say, I could scale up the x's and scale down the a's. But the physical quantity, which appears in this equation, is always k over a squared, and that's really the inverse curvature scale squared of the universe. So the first equation we got was the Friedmann equation, and you notice something peculiar about it. Only involves first time derivatives, no second time derivatives. Okay, so note here only only single time derivatives. Okay, this equation is a constraint. Okay, so we say if we get some equation that restricts the velocity somehow, that's a constraint. It's not an evolution equation. What we call an evolution equation is something which involves the second time derivatives. And so this we would call an evolution equation, like F equals ma. Second time derivatives. Okay, and in general, this is how the Einstein equations work. It's always true that the G0 beta equations are constraints. Okay, so let's write that out as G00 and G0I. These are constraints, and the Gij equations are evolution equations. So they tell you how the velocities change. Okay, so let's discuss some general, the general solution to these equations with certain simple types of matter. Okay, so for simple types of perfect fluid, P is a function of the density. So if you know the density, you can predict the pressure. For example, dust or pressureless fluid. Just has P equals 0. And then we saw that equation for stress energy conservation, the rho dot equation, implies that rho dot is minus 3 a dot over a rho, and that implies that rho is some constant over a cubed. And we'll call it Cm. So the constant for matter. Okay, so this is going to be non-relativistic matter. Matter. And you can think of it as a gas of particles, i.e. gas of particles with V much less than C. With V much less than C. So there's there's negligible pressure. And then all that happens is the universe expands and the density of the stuff falls, like 1 over a cubed, just as you'd expect. Okay, the mass, total mass in a co-moving volume. Okay, so co-moving here means a volume in X. So if you just cut out a chunk of the universe in X and call that the volume, then it's co-moving because it's going to be blown up by the scale factor A. And the total mass in a co-moving volume is proportional to rho a cubed, which is constant. So that's the very simplest case. And what we call cold dark matter, which is still mysterious, but it's some form of matter that dominates the gravity of the universe on large scales, on scales of galaxies or clusters of galaxies. This matter behaves exactly like dust, as far as we can tell, to very good accuracy. Okay, so this is e.g. cold dark matter. And we still don't know what that cold dark matter actually is, but there are some plausible candidates. Second example is radiation. And so this is e.g. photons or massless neutrinos. And these obey pressure equals 1/3 rho. Okay, so if you study the thermodynamics of a gas of relativistic particles, as described, for example, in Landau and Lifshitz, and you construct the partition function and from it work out the pressure, you'll find that the rho, the density goes like some number times temperature to the 4th, and the pressure is 1/3 rho. So this comes from the statistical mechanics of massless fields. And so what this means in that, so what we have is that rho dot is minus 3 a dot over a, rho plus 1/3 rho, which is minus 4 a dot over a rho. And so rho is equal to some constant over a to the 4th. So the constant measures the density of the radiation when the universe has a certain the density scales as 1 over a to the 4th. Note there's an extra power of 1 over a, and one can understand that extra 1 over a because the energy of each photon decreases as 1 over A as the universe expands. So the number of photons is remaining constant. Therefore, the number density is going down like 1 over A cubed. But the energy of every photon is decreasing as 1 over A. Because the energy, of course, is h nu, which is hc over lambda. And the wavelength of every photon is just being stretched by the expansion. Okay, so the wavelength here is just literally being stretched out by the expansion. Lambda proportional to A. And one way to see this is to imagine a spherical universe or a torus, and you put a fixed number of wavelengths in the, say, going around the equator of the sphere or going across the torus, and then the universe stretches and the wave's got to vibrate, but it's not going to change the number of nodes. And so the only thing that can happen is that the wavelength stretches with the universe. And that means that the energy goes like 1 over A. Energy of each individual particle goes like 1 over A. Another form of stuff we described Sorry?
Would this imply you could somehow measure the stretching of space? Like if you could measure the energy of the photon decreasing?
Yeah, I mean, another way of saying it is the photon is not aware of the expansion of the universe. Okay, because a photon, so this relates to the comments I made a few weeks ago about conformal invariance. That the photon, Maxwell's equations have all these symmetries. They have special relativity, they have gauge symmetry, and they have another one, which is conformal symmetry. That Maxwell's theory, if you change the metric to any factor, any function of x times the metric, Maxwell's theory doesn't care about that. So the dynamics of the photons really doesn't know about the expansion of the universe. The only way you can tell that they don't care about the scale of the universe. The photons literally see a universe of fixed size. Now, everything else sees the scaling up of the universe. Everything else, the massive particles, their equations are not invariant under this. And so according to everything else, the universe is expanding. But really, the photons don't even see the expansion. And it's only when we emit photons and receive them. So if you emit a photon, it travels through space. As it's traveling, you can picture it stretching, and then somebody else received it. They will receive it redshifted by the expansion. So yes, you can see it, and in fact, you can view the Hubble law as nothing but a measurement of the stretching of space. So there are often in general relativity many different ways of looking at the same thing. So one view of the Hubble law, we'll discuss this in a moment, but if some star emits light and we receive it on Earth, okay, you can try to understand what happened to that photon on the way to us. And one view of this is simply that the star emitted the photon, but the space was expanding, and the photon stretched, and the photon, when it arrived at us, is red. Another view of it is to say, no, this is a bit like you tried to, that's actually a completely correct result. It's exactly correct. The calculation is exactly right. you get the right redshift result. You get that the change, you get that the frequency of the photon is proportional to 1 over A. It's proportional to the inverse wavelength. And so if it's emitted at a certain value of A and received at another value of A, its frequency redshifts by exactly this amount. Another view of this is, no, you say the star is actually zooming away from us, okay, and there's a Doppler shift. So in the rest frame of the star, it's emitted with some wavelength, but we receive it when it's emitted. If you like, the subsequent peaks in the wave are emitted further and further and further away from us. And so the frequency we see is lower. And these two descriptions are actually equivalent. And they give the same results. For small distances, they're actually equivalent. At large distances, this one is correct. The other one isn't really relativistic. The naive Doppler shift, if you just use the Newtonian, the non-relativistic Doppler shift, you won't get the right result. This gives exactly the right result. Yeah.
So if you had a bunch of stars all around you and you're saying, oh, the space isn't expanding, just everything around me is moving far away, but if space isn't expanding at the edges, where is it moving away into? Don't you still need to say some space needs to expand to accommodate everything moving away from me?
Yeah, I mean, you can, yeah. So sorry, what are you worried about where things are expanding into, or?
So you're saying it's different. One view is space is expanding, and you're
Yes.
saying the other view is the stars moving away from me.
Right.
What I'm thinking is if I looked in every direction and saw a star moving away from me,
Right.
and then if space isn't expanding, but every star also sees everything, if everything in the universe sees everything around it moving away from it,
That's right.
and then along the edges, where is it going in? Yeah, so where is it going into? Doesn't that also mean that space is expanding eventually?
Right. I mean,
But I guess not everywhere. At every point in space, it's not expanding. That maybe.
points are not expanding, but space distances are expanding.
Maybe everything moves away, and just at the edges, we super stretch.
There's no edges, right? There are not necessarily any edges.
Yeah, I mean, I was trying to think of the different. If I'm trying to say right here, nothing's stretching nearby me, but maybe far away there's a problem, and so over there something else happens to take all this stuff that's moving. Right.
I mean, you can get into these worries. I mean, I think the thing to go back to is that general relativity is a local theory. It says space-time is locally flat, looks like a metric. And what this G mu nu does is it kind of ties together all of these points around whom every point space is flat and special relativistic physics holds. But when you go to large distances, it's in gluing them all together that this metric really does its work. So to try to translate all that back into special relativistic language when you're dealing with large distances, just a mistake. So for example, you will find that particles are traveling faster than light. If you sort of try to compare two particles that are far apart, we'll do this in a moment. I mean, we'll get Hubble's law, and Hubble's law says that recession velocity is proportional to distance, right? Now, if I take the distance big enough, I'm going to go bigger than the speed of light. And it doesn't make too much sense. So just bear in mind that the metric is the quantity that sort of glues together all these flat space-time views of physics. And so this Doppler shift, you can try to interpret it in terms of special relativistic physics, that something's traveling away from me. But that picture is going to break down at some point when that star is moving close to the speed of light away from you. And this other picture that space is stretching is actually a better one because it's dealing with the local behavior of the photons as it travels through space. Okay, so we'll come to more of this in a moment. These are all good questions, but we'll come to more of this in a moment. Let's just deal with another kind of dark energy, another kind of energy. Dark energy, or alternatively, the cosmological constant, And so I've already discussed this. It's Lorentz invariant. And that forces P to be minus rho. It has negative pressure. It's more like a tension than a pressure. And this forces rho dot to be 0. Right? So as the universe expands, the density of dark energy doesn't change at all. That's pretty weird. And so we just say rho is equal to C lambda, a constant. And so if you measure the total energy in a volume, co-moving volume, it'll be rho times A cubed. Well, A is growing, so you're just getting more and more energy. And that's fine. It's perfectly compatible with the stress energy conservation equation, which is what we've used. And this is one of the mysterious things about gravity, is that it allows a form of energy whose amount will just grow and grow as the universe expands. It's even weirder than that, because if this rho is constant, we can go back to the Friedmann equation and let's assume k equals 0 for simplicity. So assume flat space. It's pretty much the same for the other cases, but for flat space, you see you've got A dot over A squared equals 8 pi g over 3 rho, or 8 pi g over 3 c lambda. And the solution of that is just that A grows exponentially. E to the h, let's call it h lambda t, where h lambda squared is 8 pi g over 3c. So in fact, not only do you get more and more energy, but the universe actually grows exponentially if it only has this dark energy or cosmological constant in it. And so you get exponentially more energy as time proceeds. And so that's why this is the basis of the theory of inflation, which postulates basically a temporary form of dark energy with a very high density. And this temporary form of dark energy causes the universe to grow exponentially in size. And this is why it was called that the universe might be, it was said that the universe might be the ultimate free lunch. Yeah.
So I guess kind of related to that, is there some requirement when we find energy like this that it not be able to interact with ordinary matter, or can it?
The Lorentz invariance is a very serious constraint on it. So you could ask, is it possible for the dark energy to decay into other stuff? Now, we have ways of describing the dark energy. And one of them, well, okay, so the dark energy, in the way I described it, would be specified by some number. Okay, so P is minus rho, and then rho is a constant, so there's just some number. So there's some number filling space. Now, in fact, we know there are other fields which contribute to the dark energy, one of which is the Higgs field. Okay, so the dark energy, we now understand, receives many contributions. So there are basically many contributions to, or many different forms of energy in physics which contribute to the dark energy. One is the vacuum fluctuations in ordinary space, that every field, electromagnetic, Dirac field, they all have vacuum fluctuations. These vacuum fluctuations behave like dark energy. Another is the QCD vacuum. So in QCD, strong interactions, the vacuum is not empty. It's full of gluon, a gluon condensate. And the gluon condensate is what keeps the quarks together in nucleons. And so this gluon condensate, again, contributes to the vacuum energy. And finally, there's the Higgs field. So we have vacuum fluctuations. We have a gluon condensate. We have the Higgs field. So there's some Higgs field, H, and it has a potential energy, V of H. And this is some function of H. Okay, so H is the strength of the Higgs field. And this vacuum, V, or potential energy, or alternatively vacuum energy as a function of H, looks like this. And the vacuum we live in is one where H is not zero. Okay, the lowest energy state in the universe has the Higgs field non-zero. Okay, here. And this is how electroweak symmetry breaking works. And this is how the electron and muon get their masses. And quarks get a mass from this as well as from the strong interactions. So, we somehow live at the minimum of the Higgs vacuum energy. If you excite the Higgs field, okay, so if then you get a Higgs boson, and this decays into other particles or other forms of energy. So if you excite this guy, basically it will relax back down to the vacuum, but that still has some non-zero energy density. Now, the way we build the theories is simply to tune the minimum here to match the observed dark energy in the universe, which is a minuscule number. And so we're very unhappy about that, because that's a kind of ridiculous fine-tuning which we have to do just to get the model to fit the data, with no understanding of why we have to do that. So we're definitely missing something rather fundamental. And the problem is even worse, because if you take the results of LHC and you work out what are the properties of this Higgs potential, it turns out you can calculate them using the renormalization group and just ordinary quantum field theory. And actually, it does this. Okay, so this scale is 250 GeV. That's the Higgs VEV, vacuum expectation value. That's the value of the Higgs in the vacuum. When you get up to about 10 to the 10 GeV, the vacuum energy gets lower and actually goes negative. And there are indications that there's what we call an ultraviolet fixed point at the Planck scale, meaning that physics becomes conformally invariant. So this is the thing I'm very excited about. There's some indications of great simplicity out here. But what it means is we're not stable. Our vacuum isn't stable. And so when you said, is it possible to change that vacuum energy, indeed, that's the prediction of the standard model, is that there's going to be a quantum tunneling process which will carry us from this vacuum out here. So in quantum mechanics, a particle can tunnel out of a barrier. Well, if you have a field, and it wants to sit here classically, that's the minimum energy, wants to sit there everywhere in space. Well, what happens is that locally, in one region of space, just at random, the field will quantum fluctuate through the barrier. So you have a little bubble with a little pocket where the Higgs field has a large value. And then this pocket turns out, essentially because P is minus V, the pressure is minus the energy density. And so if V gets lower, the pressure is more positive, okay? And so this little pocket has high pressure. And basically, it just grows at the speed of light. And it will take over the whole universe. So the prediction is that in 10 to the power 600 years, this is going to happen. Okay, it's pretty exciting. And actually, just to be speculative, personally, I believe at some point we will actually use this. I mean, there is essentially unlimited energy stored in space, if only we can figure out how to use it. It's a little bit dangerous. Engineering with the universe. Okay, so this is the dramatic effect of exponential expansion of the universe. And people noticed this in the 1920s, that a lambda, you see, this cosmological constant is just given by adding, so T alpha beta equals lambda G alpha beta. It's the simplest form of energy you could imagine, where the stress energy is the metric. So people thought about this in the 20s, in fact earlier. It was Einstein's first cosmological model, as I'll show you right now. And then when the universe was realized to be expanding, they said, aha, maybe this lambda is really what's pushing the expansion. And so this idea has kind of recurred again and again. And then finally, in the late 1990s, lambda was measured and found to be positive. Okay, so let's put all this together. We've got matter, we've got radiation, we've got cosmological constant or dark energy. Let's put all that together. The general solution with matter, radiation, and lambda. So we'll write this in the following way. A dot squared, so Friedman, we can reorganize the Friedman equation. By the way, Friedman, the history of this is just amazing, that Friedman was working in then Leningrad in Russia after the revolution. Very young guy. I mean, I think he was doing his PhD. And he heard about Einstein and Einstein's equations, and he thought of solving time-dependent equations. And he found these solutions, and he sent them to Einstein, and Einstein said, it's obviously wrong. Your mathematics is up the creek. And Einstein didn't believe it at all because the solutions are singular. So he thought these are not really solutions. It was a very intense debate. And finally, it turned out that Friedman was right. And yes, the universe is expanding and comes out of a singularity. So the Friedman equation, it's good to reorganize it like this. Rho matter plus rho radiation plus rho lambda times A squared equals minus K. Okay, so all I'm doing there is taking the Friedman equation, multiplying by A squared, and pushing the rho term on the left, and keeping the K term on the right. And then these terms individually, so this together, so rho times A squared, this will be Cm over A plus Cr over A squared plus rho lambda A squared. Okay, now the reason I wrote it like this is this is the equation for the energy of a particle moving in this potential. Okay, so CF 1/2 mx dot squared plus v of x equals E. Okay, and so if we pick m equals 2 and x is A, then you can see this equation is, and K is the energy, then this equation is just the energy of a particle moving in a potential. And to understand the general solution, we just have to plot the potential, and then we can immediately see what the general solution is. So here m equals 2, and v effective of A is equal to minus 8 pi g over 3 Cm over A plus Cr over A squared plus C lambda A squared. So let's make a picture of that effective potential. V effective of A, this is A. You see I've got a minus 1 over A from the matter, minus 1 over A squared from the radiation. So what is the shape of the curve at small a? What does it look like? Negative. Okay. Obviously, the radiation is going to dominate at small a. So this is going to be 1 over A squared. This is the radiation. This is 1 over A. This is the matter. Okay, these are going to dominate. And then at large A, right, at large A, these guys go away. Large A, this one dominates. So it goes like minus A squared, dominated by the lambda. Okay, and it's always negative, provided C lambda is positive. Cm and Cr are positive because radiation and matter have positive energy densities. But C lambda, let's assume it's positive. This is going like A squared, which is lambda. Yep.
You're saying assuming C lambda is positive, right?
Yes.
So is there a possibility that C lambda is negative?
Yes.
But in this case, I have no expansion of the universe, right?
No, if C lambda is negative, in fact, you have a collapsing universe.
Yeah.
Right. So lambda being positive, this solution here is called de Sitter space, or de Sitter space-time. In fact, we've studied it before. We mentioned it earlier. This is the space of maximal symmetry. We happen to be studying it on the flat slicing. If you have lambda negative, you have a solution called anti-de Sitter space-time. Okay. So if lambda positive, you have de Sitter space-time. And lambda negative, we have anti-de Sitter space-time. And yeah, but from this point of view, if lambda was negative, you see this potential would go like this if lambda is negative. And so the universe would run out here and then collapse. Okay, if lambda is positive, the universe runs out here and keeps running out, expand exponentially. Okay, lambda positive. Okay, so just from this picture, you can see the general solution. So the energy of a particle is constant. So to see the general solution, all you do is pick the energy equal to some value. Okay, so for example, this solution will be k equals 0. Okay, the energy equals 0. And what the solution represents is the particle, or the scale factor, coming out of the Big Bang, A equals 0, and just shooting over the top of the potential, because it has 0 energy, and the potential is negative. So obviously, its kinetic energy is the difference between 0 and the potential. So the particle rolls up the hill, slows down. It's at its slowest here, and then it rolls off to infinity exponentially, according to that equation. So if, on the contrary, if k is positive, then if the universe is a sphere, then the universe will have negative energy in these terms. Okay, so this is k positive, and so the ball rolls up the hill, doesn't have enough energy to get over the top, and so it falls back to 0. Or it might be over here. Okay, it might do this. It might come in from infinity, bounce off the hill, and go back to infinity. So that would be a bouncing universe. Okay. And this point here, A equals 0 is the Big Bang. And you can see that generic solutions do have a Big Bang. And finally, if K is negative, then we are, K is negative in these terms is positive energy. So let's draw it up here. It will run off to infinity. It'll just, run off to infinity. So that is the general solution of the Friedmann equation, specified by a single number, k. Now, as I told you, you can pick k to be 1, -1, or 0. You can alternatively leave k to be a parameter. So basically, it's possible to rescale k by rescaling a, all right? Or you don't need to. You see the way a enters this equation. If I rescale a, I can set k equal to 1, -1, or 0, but I don't need to do that. I can leave k as a parameter as well. Okay, so that's the general solution of the Friedmann equation. And so tell me where Einstein's static universe is. It's here. Okay, so Einstein's first attempt to solve the equations of cosmology, he assumed the universe would be here, the Einstein static universe. Okay, and you can immediately see k has to be positive because it's got negative energy in these terms. And you can also see, I think we worked this out last time, that the density of matter has to be twice the density of lambda. Okay, you can see that somewhere. You see a double dot has to be 0. If you're sitting at the top here, a double dot is 0. So certainly you've got rho plus 3p would be equal to rho lambda minus 3 rho lambda plus rho matter, right? Because p for lambda is minus rho lambda. P for matter, when you have rho plus 3p, you just add the different components, okay? And this has to be 0. So rho matter is twice rho lambda. And furthermore, you can easily tell that the radius of curvature, which is a over the square root of k, is equal to 1 over square root 4 pi g rho matter. Okay, so the static universe exists where the matter is pulling it in, the lambda is pushing it out. It's very delicately balanced at a particular size. What's wrong with that universe? It's not particularly stable, is it? If you balance something on the top of a hill like this, it can fall off. And that's exactly what happens. That if you take this universe, which is homogeneous and isotropic, but if you imagine in some little region of space, the scale factor or the metric gets a little bit blown up, then it's going to fall off the hill that way. And if it gets a little bit shrunk, it's going to fall off the hill this way. And so soon after Einstein proposed this, Eddington, who was in England, analyzed the equations, including the possibility of time dependence, and showed that the Einstein static universe was unstable. And Einstein then called then said that the introduction of the cosmological constant in the equations, which he used to get a static universe, was his greatest blunder. Okay, but then, of course, nearly a century later, that great blunder was verified, that there really is a lambda, and his static universe is pretty close to the real one. I mean, the real one, this is the real universe. We're sailing over the top of this hill. In fact, currently, we're about here on this curve. Okay, currently, if you work out the matter contribution is a curve like this, the lambda contribution is this curve, and currently, today, let me just do this properly. So today, so if we want to compare this equation with observations today, what we do, okay, so let's say, let's compare with observations. So to compare with observations, I want to rephrase the equation in terms of quantities which can actually be measured. And we just divide by a squared. So a dot over a squared minus 8 pi g over 3 rho m plus rho r plus rho lambda equals minus k over a squared. In fact, I'm going to put that, I'm even going to bring that over here, plus k over a squared equals 0. This quantity is known as the Hubble constant squared. H equals Hubble constant. And the reason for that is that if we consider points, well, let's say particle or galaxies or stars at fixed x. Okay, so we've got this metric as a function of x. Now, these particles or stars or galaxies are going to obey the geodesic equation in x. You can easily check that the geodesic equation allows a solution in which x is constant. You just think of the space, and you put your particles on it, and the particle positions are just fixed at a given x. So that is a solution of the geodesic equation. And then so that is solution of geodesic equation. The separation of points at fixed x grows like a of t. Okay, because the distance between points is measured by the metric, so the distance squared is just going to be d squared equals a squared of t, delta x squared. And so d dot over d for any particle, the velocity, the rate of recession divided by the distance is equal to a dot over a. And so that tells you that d dot equals the Hubble constant times d. And so that says that the recession velocity, recession speed actually, speed is proportional to distance. So if all of space is expanding, then the further away an object is, the faster it's moving away from you. And this, of course, is Hubble's law. Okay. And so Hubble verified this in 1928. He measured d dot. Hubble, 1928. Hubble was very lucky. He had access to by far the biggest telescope in the world. And nobody else could do this. He could see very distant stars, and he could measure the frequency of their spectral lines, and he could see that the further away you went, those spectral lines were shifted more and more red. Yeah.
Sorry, can you just remind us why A dot over A is in fact constant?
It's not a constant, it's a function of time.
Oh, okay.
Yeah. Okay, so it's a good point. Okay. In this equation, D is a function of time. D is a function of time, and A is a function of time. When we say Hubble's constant, it's not constant. Okay. So it should be called maybe Hubble parameter. I don't really like that either, but some people call it the Hubble parameter. Hubble constant or parameter. It is a function of time. Okay. It's only a constant in the sense that it's the proportionality constant between the d dot and the d.
So we use it to compare things at different distances.
Exactly. Exactly. That's all. At the same time. And so what Hubble did is he measured the recession velocity of galaxies versus their distance. And the way he got the recession velocity was from the Doppler shift. Okay, and this was all for distances so that these recession velocities are much less than the speed of light. So we don't get into the issues regarding the incorrectness of this sort of even pre-relativistic view. So these are all for small velocities. And d dot against d, he plotted a curve, and the data roughly went through that curve. Okay, now in fact, Hubble measured h, this number h, to be 550. You see, it's a speed because it's a ratio of, it's a speed divided by a length. So it's given in units of speed, kilometers per second per megaparsec. 1 megaparsec is 10 to the 6 parsecs, and a parsec is approximately 3 light years. Okay, so it's a distance. And so the Hubble parameter is given in units of speed per distance. And he measured 550. Now today, the actual value measured today is approximately 65, plus or minus, I think, 10 or so kilometers per second per megaparsec. Substantially different. Okay, so this is what he got all the accolade for, but the slope of his line was almost a factor of 10 wrong. Okay, nevertheless, his result was correct. It's maybe very good luck. But the reason he was wrong is that he misidentified groups of stars. He thought a group of stars was actually a single star. And so he was mistaking a group of, say, 5 stars or 10 stars and thinking it was actually a single star. And so the star appeared to be much brighter and much closer than, in fact, it was. So when better telescopes came along, people realized these are groups of stars. So even though his slope was wrong, there was just a factor of 10 calibration. The fact that it was a straight line was the important thing. Yeah.
Quick question. If we write h squared as a dot over a squared because we want it to be positive, or does it have the same sign as a dot over a?
No, that's a really good question. H observational is plus. Okay. And we define, yeah, sorry, I didn't really define H, did I? Let me define H. Whoops. By definition, H is equal to A dot over A. Okay, can be positive or negative. Okay, so we just define it to be the expansion rate of the universe, and if it's negative, we interpret that as the collapse rate of the universe. So certainly at the time of Hubble, there was no explanation for why it was either expanding or collapsing. It could have been collapsing. So when this was discovered, then suddenly this diagram became very important. And people realize that, you know, for some reason we're on a trajectory where A is increasing. Yep.
How concerned are we about making such like global statements based on this local theory? Like, I guess, like how do we know that we're on the right track?
Right. Well, the cosmological principle is a gigantic extrapolation, right? It just assumes that the universe is the same everywhere. And yeah, we should be very concerned about that. We can only see a certain distance in the universe. In fact, if the right way to phrase that, we draw a picture. So we've seen that A hits 0 in generic solutions. There are some bouncing solutions as well, but observations seem to indicate we're in this k equals 0. Observations indicate k equals 0, and there's no bouncing solution for k equals 0, and we seem to be expanding. So what does that mean? Because as we follow back A back to 0, you know, it hits 0. And Einstein's theory fails because the metric is 0, or rather, the determinant of the metric is 0. The metric's not invertible. That's a Big Bang singularity. Another way to look at it is we sit here at some point in space-time. Here are these coordinates x, the spatial coordinates. We can think of following a light ray back, or just looking out in the sky. Okay, so if I look out in all these, in all directions, in a picture like this, I can represent it by saying just 2 directions. Okay, if I try to represent a 2-sphere by a 0-sphere, which is this is, then there's just 2 directions. So we're looking out. I guess I could even rotate this around. So we're looking out in all directions on the sky, and these light rays form a cone going out from our point backwards in time. So this would be time. And we can literally see the surface where A equals 0, the Big Bang singularity. Okay? So this is the causal structure of the universe. And the only part of the universe we have access to is this part. Okay? We really have no idea what's going on. at further distances. Now, the amazing thing is, though, that the part we can see is incredibly uniform. It really is almost the same in all directions. It varies by less than 1 part in 100,000 in density and temperature across the whole sky. Okay? So there is a mystery as to why the universe is so incredibly uniform on large scales when it had no reason to be. And that was one of the motivations for the theory of inflation, which is very popular. Personally, I don't think it does explain it, but it doesn't. I don't think it succeeds in solving this problem. But it's certainly a huge mystery why the universe is so smooth on large scales. And so all one can really say is that this cosmological principle, which was just a wish for simplicity, it's proven to be amazingly accurate. And now it's up to us to explain why it works so well. Yeah.
Measured relative to?
Yeah, okay, so I just drew a picture because I didn't want to be too technical, but let me, now that you ask, let's write the metric down. Gamma ij dxi dxj. The time one uses in this diagram is what we call conformal time. It's a time which photons see, okay? Because we want to draw a picture in which photons move at 45 degrees. Looks as close as possible to the picture in flat space-time. Now, you see, what I can do is define a new time, a of t d tau, or let's call it eta. Define a new time. Okay, so all this means is that eta is equal to integral dt over a of t. Then d eta will be dt over a of t. And so then the metric becomes a squared of eta now, because I changed coordinates from t to eta, times minus d eta squared plus gamma ij dxi dxj. Okay, but then I told you that photons actually don't care about this factor. Okay, and we'll see that in a minute when we study the action for a photon. So invisible to photons. So this is the metric the photon sees. It doesn't have any expansion at all. Okay, so you could imagine just Minkowski space if gamma is the flat is E3. This is just Minkowski space, and the picture I'm drawing is just the lines for a photon in Minkowski space. Alternatively, if this is a sphere, you can imagine a sphere of fixed size that just sits there forever, and the photons move around it at the speed of light. Okay, and again, there would be this picture that I simply can't extrapolate. So you see, in the conformal picture, there is no Big Bang singularity, right? In the conformal picture, there's no singularity here. You can just extrapolate this into the past. Okay, what's singular is this guy vanishes at that point. So your description of matter and everything else is having big trouble at the singularity. But the photons aren't having any trouble, and you could just extrapolate them right through. So, but in the conventional point of view, one should just stop here, because the theory as formulated by Einstein just fails at this point. You don't really know what to do at this point. So lots of people have ideas for how to extrapolate it. I think the idea that there is conformal symmetry in physics is the best idea, and probably right, but we still don't quite know the right way to do that extrapolation. Okay, so, but in any case, the only part of the universe we can see is this part. Can only see this part of the universe. And should we worry about the other part or not? It's not. It's certainly debatable whether we should worry about it at all because we can't see it. Okay. Now, so as I mentioned, I was going to come to the realistic universe. I've lost the right equation. There it is. So let me just rotate these things around. Leave this up. So let's think about that equation again. The way we usually rewrite this equation, so we can certainly measure this Hubble constant. It's the expansion rate of the universe. We can measure the density of matter, radiation, and dark energy, or at least try to infer it from many different observations. And we can try to measure the curvature of space. We rewrite this. Let's just bring it down again. Let's call it something. Let me just call it star. So conventional to rewrite star as follows. Okay, we simply divide by h squared by h squared and define 8 pi g rho matter over 3 h squared as equals omega matter. Okay, so omega matter means the density of matter in units given by Newton's constant and the Hubble constant squared. So all it represents is the fraction. So we write this equation as 1 minus omega matter plus omega radiation plus omega lambda. And actually, people write omega k equals 0. So by definition, the omegas just measure the proportion of whatever comes into the Friedmann equation contributed by that stuff, okay, whether it's matter, radiation, lambda, or curvature. And then observation indicates that let's forget the numbers. Omega matter is about 0.23. Omega radiation is 0.0003. Omega lambda is 0.6. Omega lambda is about 0.72, I believe. This is 0.28. And omega curvature is consistent with 0. So observation indicates that k is 0 within 1% or so. And nearly 3/4 of the stuff in the universe is the dark energy. Just over 1/4 is in matter. So omega m includes cold dark matter and baryons, just the particles we're made of, atoms, etc., etc. and massive neutrinos. Sorry? Omega k is the contribution of the spatial curvature to the Friedmann equation in units where everything adds up to 1. Okay, so by definition, omega k is equal to k over a squared over h squared. Yeah, I mean, this is what people like to do. I'm not really justifying it. They like to talk about omega k, and then that's a dimensionless number which represents the contribution of curvature to the universe. And as I said, observationally, one has something like omega k is less than around 0.01 or so. The universe is nearly flat, as far as we can see. Again, a very deep mystery. So, yeah.
When you say that observations confirm that omega k is of this order,
Yes.
those are observations of what?
The geometry of the universe.
So that means we can only have local access to the geometry of the universe, right?
Right.
So isn't it, I mean, any measure that I can make of the geometry of my universe will always give something that's locally flat? So
No. So imagine you're living on a big sphere,
yeah.
and you want to measure the radius of the sphere. So the way you do it is you say, I need a ruler. Place this ruler at a certain distance. Now, in flat space, the angle subtended by the ruler will be the length of the ruler divided by the distance, right? So in flat space, you have some ruler of length L, and you place the ruler at a distance d, and then in flat space, theta is approximately L over d. Okay? On a sphere, that's not true, right? Because the ruler, as it gets further, will subtend a progressively larger angle compared to flat space.
Yeah, but I mean, in the universe itself, where we are right now, up to which distance can we do that in order to see this deviation due to the curvature?
We can do it up to the Hubble radius. Okay, the Hubble radius is basically the distance. So we receive radiation from the Big Bang. And very fortunately, there is a ruler. Okay, the ruler is given by the distant sound has traveled since the Big Bang. You may have seen these curves of the microwave background anisotropy, power spectrum. I don't know if you've seen these curves. These are measurements by the WMAP and the Planck satellites. Okay. So this is as a function of L. L is a Legendre polynomial. This is basically the power on the sky as a function of angular scale. The location of this peak represents the distance sound waves have traveled since the Big Bang. And that's a physical distance. We've got a fluid full of baryons and photons, and we know from absolutely conventional physics exactly how far a sound wave has traveled. And that's what this peak is. So we have a ruler sitting approximately 14 billion light years away from us. Okay, and from the location of this in angular space, we can infer what the geometry of the universe is, and it turns out it's nearly flat. But all of this is the topic of the cosmology course, which you'll be taking later. So I don't want to get too diverted into that. I'll just be giving you a cosmology course. So, but yeah, any other questions? Is that clear?
Well, a little bit. I mean, we're saying that the universe is expanding, right? So when you say that we have this distance, when I think of a distance between two fixed points, but if the fixed points are getting even more and more.
Yeah, but I
separated.
explained that the photons,
Okay, because it's radiation.
yeah, because it's radiation, they actually just see the geometry directly. The photons really are living on a space-time cylinder, okay, where if the universe was closed, they would be, was positive curvature. If the universe was a sphere, then you can imagine space as being a sphere and time as being the direction along the cylinder. And the photons are just zipping around this cylinder, okay? And so, yeah, using photons, you can directly see the geometry of the cylinder. You need a ruler somehow, but fortunately there are lots of rulers around because there was stuff emitting radiation and there were sound waves and so on. So the progress in this subject has just been incredible the last 20 years. And you might also say, how do we see the dark energy? How do we see lambda? Okay, it's dark. You can't see it, okay? And it's completely uniform, all right? And no ordinary physics is sensitive to it at all. The only physics sensitive to the vacuum energy is gravity. Because in ordinary physics, you know, I have this dark energy filling space, and I do some physics experiment. Well, energy is conserved, and so I send some particles in and some stuff comes out, but the dark energy was there before and it's there afterwards. It makes no difference. Could be any value. Doesn't make any difference, okay? So you could say, how on earth am I going to see this stuff? So you see it, first of all, in the expansion of the universe. That's how it was discovered, by supernovae redshifts in the late 90s. That's the most obvious way to see it. And then myself and my colleagues in '94 proposed another way to see it, which is to look at the clustering of galaxies. So imagine you've got a cloud of stuff, and it is slowly condensing into galaxies and giant clusters of galaxies. And now we are looking outwards, and the radiation coming from the Big Bang travels through this cluster. Okay, so this is a clump of matter. So there's a gravitational potential well, right? Now, if the universe was not expanding, and if the potential well was static, then the photon would fall in, and it would climb out, and there would be no gravitational redshift. We wouldn't see anything. Okay. However, the universe is expanding, and if there's a lambda, it's beginning to expand exponentially. Okay, that's pretty dramatic. So what happens is the photons fall in, and then these are a very big region, and then the lambda dominates and rips this region apart through its repulsive gravity. And so basically you get the blue shift as the photon falls in, and you don't get the red shift as it falls out, because this thing is pulled apart. So you can calculate this effect, and what it means is that there should be a correlation where I see a clump of galaxies on the sky. Behind that region, I should see the microwave background radiation appear a little hotter than elsewhere. Okay, and this was measured, and the amplitude of it is exactly what you expect if there's a lambda. So this was an independent measurement of lambda. It's now accurate to 5 sigma. So we have independent ways of seeing lambda, but they're indirect.
One other thing, I mean, for example, is omega and omega r, and I can understand that you can put it in the equation with physical ground, right? One is radiation, the other is ordinary matter. Here, we assume that P equals minus rho, which is a solution to the Friedmann equation, right?
It's not the Friedmann, it's
to the
stress energy conservation.
Right, okay.
Okay.
So, and this gave rise to this cosmological constant and dark energy. But isn't there another kind of solution to these equations that I can find in which rho and the pressure are related in a different way, and I can also interpret it as another type of matter that I cannot see?
There are thousands of models. Okay. The cosmology literature has thousands upon thousands upon thousands of models. They are not, most of them are not very well motivated. You can easily dream up. A typical thing people do is dream up more scalar fields. So we have the Higgs field. Now we know this exists. So that's an excuse for imagining, well, maybe there are many more. And these scalar fields can have all kinds of energy, the potential energies. And if they're flat and positive, they can look like dark energy. So you can play all kinds of games. But in the end, you know, the question is how convincing is that theory? At the moment we're at, this is all we have evidence for. There's no evidence for any one of it. So there's something called quintessence. It's another kind of dark energy, which is a bit more involved than a cosmological constant. And people do the same thing with many other kinds of fields. I mean, it's fun to play with all these things. But at the moment, we don't have any evidence for anything beyond what I've said. Okay, so I want to do one last thing, which is to show you how the age of the universe is predicted by the solution of the Einstein equation. Okay, so the age of the universe okay, so let's take the simplest case. Matter only. And k equals 0. Okay, so here we have that a dot over a squared equals 8 pi g over 3 cm over a cubed, right? Matter-dominated universe. And so here I can just integrate the equations of motion. So you see, just multiplied by a dot squared equals a constant. And so this means that a to the 1/2 a dot equals constant. And this means that a to the 3/2 equals constant times t. And so this means that a goes like t to the 2/3. So if you have matter only in the universe, then the function a is very simple. A of t looks like t to the 2/3, which basically does this. Okay? And now if I know that a goes like t to the 2/3, I can actually predict the matter density. I'll just plug it into this equation, and you can see that rho matter is 1 over 6 pi gt squared. So at a given time, you can predict the matter density in terms of the time. And even easier, you can see that the Hubble constant, which is a dot over a, is equal to 2 over 3t. Okay, so the age of the universe is just 2 over 3 h inverse. That's the age of a matter-dominated universe. Now, we've measured the Hubble constant, 65 plus or minus 10. As I said, it's a velocity per, sorry, that should have been per megaparsec. It's a velocity per distance. But of course, that's the same as the inverse time, right? Because I've got distance over distance. So h is just 1 over time, because it was defined to be a dot over a. So h dimensionally is just an inverse time. And so this equation is dimensionally correct. Now, in fact, h inverse, if you work it out, h inverse equals a time equals, it's about 15 times 10 to the 10 years. Okay? So a matter-dominated universe would be, 10 to the 9, would be 10 billion years old. Now, there are stars in the universe that are 12 billion years old, okay? According to stellar observations and stellar evolution theory, there are stars which are older than 10 billion years old. And so that immediately implies that the universe cannot just be a matter-dominated universe. But we now know that's fine because we know it involves dark energy. And I just want to give you the age of a universe with matter and dark energy. So with matter and dark energy, and k equals 0, we can use the Friedmann equation here. So I'm just going to take the rho m and rho lambda, delete the k term, delete the radiation term, and solve for t. We get that t equals integral dA from 0 up to a over square root 8 pi g over 3 cm over a plus c lambda a squared. That's the age of the universe. That's the time which has elapsed since a was 0. This is equal to 1 over h. So just change let me see, how can I say this? We can, we can set a equals 1 today. So a is an arbitrary scale factor, and we can always choose units. You see, well, if I ignore that k term, this equation is homogeneous in A. I can rescale A to set A equals 1 today. So actually, I can write this the following way, as 1 over h integral from 0 to 1 dA over root omega m over a plus omega lambda a squared. So what I did here is I pulled out 8 pi g over 3 rho matter today and rho lambda. Well, I rewrote them in terms of h, and then I pulled out the factor of h. So the time of the age of a lambda-dominated universe is just the inverse Hubble radius, the same as the matter-dominated universe, but the factor of 2/3 gets replaced by this integral. Okay, and then if I choose change variables so that a equals x to the 2/3, turns out to be the right change of variables. This is 2 over 3h integral 0 to 1 dx over square root omega m plus omega lambda x squared, and that's equal to 2 over 3h 1 over omega lambda to the 1/2 power, and then arc sinh of omega lambda over omega matter to the 1/2 power. And when you put in all the numbers that I gave you for omega lambda and omega matter, it turns out this is 1 over h for observed values. And so the age of the universe, I think I should have put 14 billion years up there, in fact. So this turns out to be 14 times 10 to the 9 years. So let me just correct that 15 to 14. Okay, so you can see that the presence of lambda makes this integral a little bit bigger. The presence, because if you look at that integral over dx, if omega matter was 1 and omega lambda was 0, that integral would just be 1, and I'd get the 2/3 h inverse result. But when omega lambda is non-zero, you pull down the omega matter, okay, and then omega lambda x squared is made smaller because x is less than 1. So basically, by introducing omega lambda, you make the denominator smaller, and so you make the integral bigger, and that's why the age of the universe is older when there is a lambda present. So even in the early, in the 1980s, when people hadn't measured the supernovae, there was still this paradox that the age of the oldest stars seemed to be a bit too old for the age of the universe. And so that was one of the earliest clues that actually there was dark energy. And in time, that was confirmed. Okay, any other questions? Yeah.
Just for curiosity, how do you calculate the time of a star? I mean, the age of a star.
So there's a very elaborate theory of stellar evolution, which was developed by Chandrasekhar and others. And so what you have to do is model nuclear processes which drive the energy of the star. You couple it to gravity. As the star collapses, it gets hotter and hotter. And so one can calculate from pretty much from first principles, I mean, with what is known about nuclear physics and atomic physics, using GR, you can calculate the evolution of a star. And so this is a very well-developed theory. And so from observations of stars, both in our galaxies, in other galaxies, fitting to the evolution curves predicted by theory, which are quite complicated, one can infer how old stars are. And the oldest stars occur in objects called globular clusters, which we believe to have formed before galaxies. And so these are clusters of stars, of very old stars. They're very stable. They just sit there and orbit each other. And from observations of the spectra of those stars and the distribution of them, one infers that the globular clusters are probably 12 billion or so years old. And so in the 1980s, the most popular model of the universe was lambda equals 0, omega matter equals 1, the cold dark matter dominated universe. That was the most popular scenario. And that predicted an age of the universe of less than 10 billion years. And then there was a worry that some of these stars seemed to be too old. So people could just say, oh, well, maybe they don't really understand stellar evolution theory. But it was a worry. And typically in cosmology, you know, nothing is known with absolute certainty. Okay, far from it. It's amazing we know anything at all. But we become convinced of things when there's enough independent lines of argument pointing to the same observation. And for dark energy, I think there were lots of, you know, what really makes something convincing is if a prediction is made from theory before the observations, okay, and then the observers go out, they look for this predicted effect, and it's there at exactly the level that was predicted. And that has happened with the dark energy in a number of respects. Our calculations showing that there's a correlation between the mass distribution and the microwave background, and there are several other such calculations. So at this point, I don't think anybody seriously doubts, within the cosmology community, doubts that dark energy is most of the stuff in the universe. Still may be wrong. Yep.
For small age, the radiation front seems to be dominating.
Say that again?
For small a,
Yes,
the radiation term seems to be dominant.
absolutely.
In that case, shouldn't we include the radiation term if we want to calculate the H of the universe?
Yes, good point. Okay, so let's do that. Okay, so I'm not sure why it's doing that. I'll do it here. So you're right. T equals 1 over h integral. Let's put in the radiation, right? So it would be dA over square root omega radiation over a squared plus omega matter over a plus omega lambda a squared. Okay. So just put it in there. Now, you can see it's true that at small a, this guy dominates over that. However, at small a, this makes it big. It makes the denominator bigger. Okay? And so it's not going to give much contribution to the integral. At small a, this guy was already big. So if we plot the integrand, okay, at small a, this one dominates. So the integrand will go like a to the 1/2. Okay, so the integrand is doing this at small a. And then at large a, the integrand's going like 1 over a. So the integrand looks like this. Now, if I put in the radiation, what it's going to do is steepen this curve so it doesn't go like square root of a here. It goes linearly with a. Okay, so you've got a square root and then linear. So that would be the radiation. Okay, and you can tell exactly where it's going to happen, but clearly it's not going to change the integral by much. Basically, yeah, at early times it dominates, but the early times are early. And the radiation, what we know from measurement, you see the radiation, something you can predict immediately, is the ratio of those two terms. So see, if a equals 1 today, right, Cm over a cubed compared to Cr over a to the 4th, well, if a equals 1, then Cm is whatever it is, 0.28. Okay, so Cm equals 0.28, and Cr equals 0.0003. Okay, so we can predict. Now, so today this is tiny. But as we go to smaller a, this guy's going to win, right? Because it scales faster. So you can ask what a does, for what a does radiation dominate? Okay, and it's for a less than C. Okay, so I say this is bigger than that, so it means A is less than CR over CM. Okay, if A is less than CR over CM, then this one will dominate over that. Now, CR over CM is approximately, divide this by that, we get 10 to the minus 4. I hope. 10 to the minus 3. Yeah. I may have missed out a 0 here. Okay. I'll try to give you a more accurate number next time. But from this number, it says 10 to the minus 3. Okay, the real number should be something like 6,000, not 1,000. But it's basically saying when the universe was 1,000th or 1/6000th of its current size, radiation became more important than matter. And that's called the epoch of radiation domination. Before that time, radiation dominated over matter. Any other questions? Do you have a problem class this afternoon? Is it in GR? Oh, it is. Okay. What time? Okay. All right. I will try and come by this afternoon. Do you have a lecture at 11? Okay, good.